All right, let's begin. So today we're going to be talking about the chaos, energy, and conservation laws. And so first we're going to begin with some review. Last time we talked about a few key terms. We have dynamical systems, which are changing in time. We have nonlinear systems, where change in output is not directly proportional, right? Like in the linear systems, you have direct proportion, but in a nonlinear system, that is not the case. And then chaos is when we have aperiodic and unpredictable behavior in deterministic system. And then you have the key idea of the phase space, which is just visual representation of states, trajectories, or solutions of a system, right? As we discussed these key terms last time. And we also talked about a mathematical example in which we were solving this differential equation, x prime equals to sine of x. And we were looking at how we can get intuitive idea of this equation using the phase space. And we were looking at our x against x prime plot over here, and how it was convenient to think of it as like a particle on the x-axis here. And we looked at like stable points and unstable points, and then we used that to construct like that small plot at the bottom. It's a bit small, but you can see how we can come up with an analytical picture of t against x, right? We kind of dropped a bit of time information, but we were able to look at like the long-term trajectories of the system using the phase space. So ultimately, phase space really helped us to simplify our ideas regarding this differential equation. We also looked at some ideas regarding the pendulum here. We looked on the left, you can see kind of a free body diagram for the pendulum. You can look at the pendulum in its position here. And we were looking at polar coordinate. And we were able to look at this. So we have from the free body diagram that the mass times the acceleration is negative mg sine theta if you use this coordinate system. So there's nothing going along the r hat direction, right? Along the r hat direction, you have like t minus the mg cosine theta equals 0. And then along the theta hat direction, you can get this equation basically. And then if you make the substitution, you know how like a is equal to r alpha? If you make the substitution, and then you use L in this case for the length of the pendulum, and then you divide out the L. So that's basically how you get this differential equation here after the masses cancel. Right? And then here you can see we were looking at this slide, right? And we were looking at different pictures of the phase portrait of pendulum without friction, right? Where it's going to go like in a loop basically, because it's not like losing any energy. So it's going to go on like a loop here. Or so there are cases where it can go over the top. If they have like very high enough velocity, the pendulum can go over the top, right? And it'll keep going over the top because it's not, there's no friction, there's no damping on the pendulum. Also a little bit at nonlinear pendulum with friction. We didn't have as much time to cover this, but basically the idea is regardless of where you start, you'll always end up at a fixed attractor, right? And they're kind of periodic. So if you can start, around the origin, if you're close to the origin in the phase space, you'll always end up at the origin because it's a fixed attractor. But there's also like points like, for example, like 2 pi away, like along the period. There's like points, there's like other fixed attractors along this theta axis. There are a few more according to the period of the pendulum, right? You get these fixed attractors. So we'll look a little bit more at the idea of fixed attractor, but let's check out Mr. Nauman's video where he'll reinforce key ideas. And so he'll reinforce a lot of the key ideas. He'll also show you guys like the damping term and like the forcing term and a few key concepts. So I will open up the chat. So check out this video. We're going to check this video out for about 5 minutes, guys. And there's the link in the chat. And it's a really cool video by Mr. Nauman explaining chaos. I'll give you guys 5 minutes. All right, so hopefully you guys enjoyed the video. It's a very interesting video where Mr. Norman was showing like different kinds of plots of like phase spaces, right? In different cases of the pendulum. So yeah, hopefully you guys enjoyed the video and learned from the video. We would trust that you were watching the video. And now we're gonna go to predicting the weather. And which was, we kind of got into this last time, but we didn't really get much time. We were cut a bit short. So let's review this slide. So in the 1960s, you have Edward Lorenz who wanted to predict the weather. And he wanted to understand why it was very difficult, right? And so he had like 12 equations and 12 variables. And he had time steps on his computer. And the computer was like showing like the time steps and different values of these different variables in time, right? But he saw that the printer rounded to 3 decimal places, but the computer calculated with 6, right? So originally he was doing a simulation for like 50 time steps. And then he wanted to like go over his results. So he went like halfway through, right? And then did it again. But he found different results in his simulation, right? And that was actually because of this rounding, right? And sensitive dependence on initial conditions. So he tried to see basically where this chaos was coming from. He tried to see where the chaos was coming from, so he made an analog and a simplified model of convection regarding 2D atmosphere heated at the bottom and cooled at the top. So he was able to see chaos and the divergence of results. So he created a simplified model of the convection rules in the atmosphere, right? So these are the equations associated with the model. We won't focus too much on the mathematics here, but more on the visualizations, which are coming up shortly. But here you can see X's rate of convective motion, Y will be the temperature difference between ascending and descending currents. And then Z is distortion from linearity. And then sigma, R, and B are basically just parameters in the system. I put some information about that down here. And then dot is just a derivative with respect to time, a shorthand. So let's look at this source. We put the source in the slides so that you can access it later as well. But here we have this source, which shows us more about Lorenz Attractor. So this is another phase space in terms of these 3 variables, X, Y, and Z. You have phase space here, which shows like the possible trajectories of the solution. And you can see there's like the butterfly pattern. It's called the butterfly effect because like these look like butterfly wings kind of. And so here you can see there's a particle traversing on the phase space, showing the trajectories, right? If you think about it kind of like parametrically, it's just showing this particle kind of moving along the phase space. And here you can see Edward Lorenz was studying the weather here and his convective rules in the atmosphere. You can see it's cooled from the top and it's heated from the bottom, right? And here there's a little bit more information about parameter Z, which is distortion from linearity, right? They're showing what does linear temperature gradient look like and what does nonlinear temperature gradient look like as well. And here they have a cool quote which describes more about the computation and the chaos that was occurring, right? We wanted to repeat some of the computation, so we stopped the computer, right? The numbers printed were nothing like the old ones. And the numbers that I typed in were not the exact original numbers, but were rounded off values. The initial round off errors were the culprits, right? Steadily amplifying until they dominated the solution. In today's terminology, there was chaos. So let's look a little bit more at that idea with some cool visualizations of chaos. So first we have the applications of the Lorenz equations. Like there's a Lorenz water wheel, which is basically a water wheel which works according to these equations. So we'll look a little bit at the water wheel. And you can also see them in models of lasers. And you can see the equations in models of dynamos, which are like in the hydroelectric dam, for example. It will convert mechanical energy to electrical energy. So let's look now. We have this water wheel. And there's a cool video regarding this water wheel. Someone basically built this, right? Like here you can see how it works. You have like water flowing in from the top here, and you have these leaky paper cups essentially, right? And so we're going to talk a little bit more about this on the next slide. But for now, check out this video for 2 minutes regarding the chaotic water wheel. All right, so we are a bit short on time, so I think we'll have to cut you off a little bit by 30 seconds, but hopefully we're able to see from the video some of the dynamics here of this water wheel, and how sometimes it can be very hard to predict, right? Where it's going. So here's a water wheel description of this, right? Here's how it works. So water is poured in steadily from the top. If the flow rate is too slow, the top will cup and will never overcome the friction, right? So the wheel won't move. But if it's faster, then the top cup will get heavy enough to get the thing moving, right? And then it'll eventually settle into steady rotation in one direction. And it can be equally possible by symmetry, which direction it goes in. And if we increase the flow rate, we can destabilize steady rotation and get some chaotic motion, right? It can rotate one way and then it can change, right? Due to like leaky paper cup, and then sometimes people place bets. But that's the basic idea behind the water wheel. And you can see the idea reinforced by this picture here. I encourage you guys maybe try to build one of these. It's a very cool challenge to try to build one of these water wheels and kind of see the chaos in action yourself. Right? You can use the information from this slide here if you'd like. And from the photo, I want to check out like a few more resources, I guess. By the way, we're citing from this book here, which is Strogratz's book, Nonlinear Dynamics and Chaos with Applications. And you guys, if you want to, you guys can get this book. It's a very good book regarding chaos and nonlinear dynamics. You guys can learn more about what we're talking about today. So here's the same water wheel kind of, this is a slightly more advanced setup. And so you can see it's sitting on a tabletop and it's kind of tilted, right? And so the nozzles will direct the water into separate chambers. So there's a lot of information about it here, right? Let's skip to this paragraph here. A sensor will measure the angular velocity and send data to a strip chart recorder, which will plot the angular velocity in time. And so you can see it rotating chaotically. And you can see this really cool plot, which gives you some idea of time against angular velocity, right? And we see the different like reversals and the unpredictable behavior here. Now let's check out a few key animations regarding the Lorenz Attractor that we were looking at from here. We had Lorenz Attractor earlier, which was phase-based, right? Regarding the Lorenz equations. So the Lorenz equations, you can see that they follow like the water wheel, right? The water wheel will follow Lorenz equations. Let's check out some animations from that YouTube video by Veritasium. So hopefully this plays somewhat smoothly. This might be a bit loud. Hopefully it's not too loud. So here we have an animation.
Here, I actually started with 3 closely spaced initial states.
So here the conditions are diverging.
So far, but now they're starting to diverge. From being arbitrarily close together, they end up on totally different trajectories. This is sensitive dependence on initial conditions in action. Now, I should point out that there is nothing random at all about this system of equations. It's completely deterministic, just like the pendulum. So if you could input exactly the same initial conditions, you would get exactly the same result. The problem is...
All right. So that was one of the visualizations. And then, so there you can see like some of the divergence of the initial conditions. And here's a little bit, here's a slightly cooler one. Here you can see a solution.
Again at the phase space of Lorenz's equations.
There's more initial conditions.
Initially, the motion is messy, but soon all the points have moved towards or onto an object. The object, coincidentally, looks a bit like a butterfly. It is the attractor. For a large range of initial conditions, the system evolves into a state on this attractor. Now remember, all the paths traced out here never cross, and they never connect to form a loop. If they did, then they would continue on that loop forever, and the behavior would be periodic and predictable. So each path here is actually an infinite curve.
All right, I'll cut it off there. Hopefully you guys enjoyed those visualizations. And then we'll continue with conservation laws.
Right, so we're going to switch gear and hope the animation is great. And this is more fundamental of the universe. So first we think in classical terms. So in classical or Newtonian mechanics, we think energy is to be definite, and this is what we learn in high school. And over time, we think that a lot of conditions in our system, isolated system, would be same. So we use conservation laws to solve for complex ideas. And this saves us a lot of time when we don't have to analyze when so I said isolated system, but even when something isn't same, for example, when force is changing in classical mechanics, we still use energy, and um, we um, we use like solve for simpler solve in simpler terms. But so this is on the next slide. When we have a isolated system, we simplify here, and when it does not change over time, this means we are observing uh, space and times are the same. And what do I mean by that? We will see later when it's changing, and we need to break out the classical terms and classical conservational laws. For now, let's see the laws we use includes conservation of energy, conservation of linear momentum, of angular momentum, and of electrical charge. So all of these, respectively, they would need something more generalized when we are seeing the history of physics when they're getting more developed and new concepts introduced. So when general relativity is introduced, you should see in the next point, the dimension of space and time are changing, and this uh, this means that the system and the conservational laws we used to use, um, they are not working anymore because over time it will change. So how do we solve that? Actually, let's think about so a redshift. This is basically a phenomenon we observe when stars are moving away from us, and their light turns red because their wavelengths are stretched out. Since the universe is expanding, and um, when these stars travel away from us, much like when a car is moving, you hear that the sound gets sharper or dimmer depending on which way they're traveling to. Their wavelengths will get stretched. And think about this, since light speed is the same, when you stretch out a wavelengths, a frequency, um, the frequency should decrease, and so its energy should change because the its path is stretching. So where does this change of energy come from? And it's certainly not conserved, because if we use the classical terms, the energy equals to Planck constant times frequency. It would not be conserved. So let's go to the next slide. And these are some of the first 2 points are two of the situations where the laws would apparently break. So redshift we discussed, and there's also the concept of dark energy. So since the universe is expanding and scientists find that they are expanding at an accelerating rate, where does this accelerating rate comes from? And so this is one observation of dark energy in our universe, and these are not conservational and not applicable to conservational laws. And there's so to think about it in more general terms, so we discussed that conservational laws are not fundamental of the universe. So what's more fundamental, we should start with the principle of least action. And think we're out of time today, but um, just briefly, this action will lead to Noether's theorem, which will characterize the conservational laws in more general terms. And they will also tell us why we have traditional conservational laws. So I think maybe next time we'll dive into this and study a bit about mathematics behind it and understand why we have these conservational laws. So yeah.
All right, thank you everyone for attending. Next time we're going to review a little bit about the conservation laws, and then we'll end off with the Kahoot as well.
Thank
Hope you guys enjoyed some of the ideas regarding chaos that we discussed today. If you weren't able to access the resources, we will keep those posted on V Clubs and on Discord as well.
Thanks, Rohan. Bye. Thanks, everyone.